Hello, everyone. I'm going to quickly go over chapter 6. I've posted the written version of chapter 6, and I'm basically just rehashing it verbally uh, and perhaps using usefully different words, different examples. We'll see. Everything covered on chapter 6 represents everything that you can expect to see in the second exam. So uh, anything in chapter 6 or before chapter 6 is fair game to appear in the exam. So the first concept we go over is independent samples t-test. This test is used for when you have two independent samples, two sample means that you want to test to see if they're statistically different from one another. And what I mean by independent is the sample means are coming from two completely different samples. So like if I'm doing a study on people and their self-esteem, and I want to know if one group of people differs from another group of people, I need a complete one set of observations of self-esteem from one group of people and another set of observations on self-esteem from a different group of people. The sample means can't consist of observations coming from the same groups of people, like a before and an after type of thing. That requires a different statistical test. And obviously, now that we're into t-tests, you might recall that the one sample t-test was used when we don't know the population standard deviation. With an independent samples t-test, we don't know the population mean or the population standard deviation for either group. We're estimating the means and the standard deviations for both groups in the sample. We want to tell if they're different from one another. So one example might be, do you think if I go to a bookstore and I ask people for a personality measure, I measure how narcissistic they are. And then I go to a sporting goods store and I ask people how narcissistic they are. Which group do you think is more narcissistic? The random people we find at a bookstore or the random people we find at a sporting goods store? I really love books and I have nothing against book people, obviously, but I kind of would have to err on the side of the book people being more narcissistic. I don't know. So that would be a time when you have one group, one set of observations and a different set of observations, two sample means from two separate groups of people. You don't know the population of narcissism of bookstore people and narcissism of sporting goods people. You certainly don't know the standard deviations. You're having to estimate both those things from the group. That's an independent samples t-test that you'd want to use in that situation. What you would not use it for is, let's say you think that going like reading a book will change how narcissistic you are. Like I think reading the latest Jordan Peterson will make you less narcissistic. So I collect a measure of how narcissistic you are before you read Jordan Peterson's new book and after you read his book. That would mean that you have two sample means. One sample mean from this group of people before they read the book of their narcissism, and one of their narcissism, same group of people after the book. That would not be an independent samples t-test. You'd need to use a different test for that. So here's where the hypothesis testing comes from. The null hypothesis, this little h with a subscript of 0, is that there's no difference between the sample means. Remember, a null hypothesis is basically, suppose I'm wrong. That's you saying, suppose I'm wrong. If the means are not different from each other, then one mean minus the other mean should equal 0. If you look at the t-distribution, the t-score, I'm going to get to that in a second, but the t-score represents how far apart the means are. When you formulate the null hypothesis, that basically says you should see 0 difference between the two groups, but because of sampling error, it's possible to see a slight difference between the groups. Even though there is no real difference in the population, there might, just because in your samples are just samples, you might see a slight difference, slightly above zero, slightly below zero. So you need to be able to assign a probability to any difference between means that you might observe. So while a difference of exactly zero is the most likely thing to see, slight differences below zero or above zero can also be seen from time to time. And these are all the different probabilities associated with seeing differences of that size. The t value that you get based on your data is going to be used as the test statistic and going to give you your p-value. This is kind of jumping ahead a little bit, but I've shaded in the areas of a t-value equal to like 3 point something. You can see that the shaded in area, this is a 3 point, let's say a 3.6 or above, cuts off this little teeny tiny area of the tail of this distribution. A negative 3.6 or whatever or lower is in this gray area down here, very small area. So 3.6 or lower, 3.6 or higher. If you add up the total area, the percent of area that these two gray areas combined take up of the total shape, like if the total shape with nothing shaded in is 100% of the area, these two little gray parts make up less than 5% of the total area. That means there's less than a 5% chance of seeing an observation this low or lower, or this high or higher when you assume the null hypothesis is true. This should sound really familiar if you're grasping the relationship between distributions, null hypotheses, test statistics, p-values. This is all the same stuff, and we're not even really changing how we're using it. We're just building on that basic foundation. So if this is sounding tricky, definitely go back and review the old material, because this is foundational. We're just talking about the same stuff and using it in a slightly different way. Now, what exactly is a t-value? So the numerator of the t-value is just the literal difference between the two sample means. But we're dividing that by this crazy acronym right here. Stands for the standard error of the difference between means. What does that mean? So basically, if you were to hypothetically keep sampling sample mean 1 of the same size, sample mean 2 of the same size over and over again, and keep calculating the differences, you would, if the null hypothesis is true, you'd expect to see differences of about 0. But since these are samples, you would see slightly higher, you'd see differences that are slightly higher or slightly lower than 0. On some rare occasions, you might see some very big difference or some very big positive or negative differences, just because sometimes extraordinarily rare things happen. The standard error of the difference between the means is the standard deviation of the distribution that you would get if you kept calculating, if you kept sampling and resampling and recording all of the differences. You'd have a distribution of differences. It's kind of like with the standard error of the mean, or the sampling distribution of the mean. It's the hypothetical distribution you would see if you kept sampling, drawing samples of the same size over and over again. You'd get slightly different means. Some means would be slightly higher or slightly lower than the population mean, but it's just a distribution of sample means. This is just a distribution of differences between sample means. That's what's at the bottom at the numerator here. So the t-value overall represents how far away from 0 are the difference between your means in standard deviation units. It's like standardizing it to where you get the probability. The t distribution gives you probabilities associated with these standardized differences. I'd go deeper into it, or I'd belabor the point a little more, but I don't test too much on like this specific kind of theoretical part of it. I do think you should understand what the sampling distribution of the sample mean is. And this really is the same thing as a sample mean. It's a distribution of differences between sample means. Really though, this is getting into the territory of more theoretical stuff, which I think is good to know for statistics. For the purpose of this introductory course, my main goal is to make sure that you know which tests are appropriate for which kinds of data and how to interpret the tests, like the p-values and whatnot. I don't need you to know the mechanics of how that p-value came about in too much exacting detail. So I don't test nitty-gritty details about standard error of the difference between means, for now at least. I do think it's important to learn, and stats is your friend. The better you know it, the better of a psychologist you'll be. But suffice this to say, I'm going to move on from here and hope that you've got it at least. You at least have some sort of intuitive understanding, even if you don't completely get this idea of a standard error of the difference between means. So here's a worked example. This is straight from the book. So let's say I have I've got 10 men overall, and I'm going to randomly assign them to groups. They're either going to be coffee drinkers or Monster energy drink drinkers. Unleash the beast. That's the slogan for Monster Energy, if you don't know. So I'm going to get a sample mean from, oh yeah, they're going to go through a speed dating gauntlet, and I'm going to ask all of their dates, how attractive did you find? Coffee drinker number 1 got a 72 out of 100. Pretty good looking or attractive. There's a difference, I guess. 38, not so much. 61, 50, 28. So like a somewhat up and down kind of group in terms of attractiveness. Drinking coffee before you go speed dating gets you about right here, apparently. Other people were randomly assigned to have a Monster energy drink, Unleash the Beast. And overall, they seem to be a bit higher. So the mean for the coffee drinkers is 49.8 units of attractiveness. And for the Monster drinkers, the mean is 85.40. So that's a pretty big difference. The raw difference, just the mean from one group minus the mean for the other group, is negative 35.6. So that's the raw difference in means. But for the t-value, we're going to place the t-value on this distribution, and we're going to ask, what's the probability of observing a t-value that high or higher when you assume the null hypothesis is true? And we don't put the raw scores on there. We want the standardized scores on there. In the book, I go into the formula. The formula is not super important. You end up getting a 10.72 is the standard error of the difference between the means. That's a way of representing how spread out, if you were to keep sampling from the population distribution of coffee drinkers and Monster drinkers, getting their attractiveness, sample sizes of 5, keep collecting them and then calculate the difference, sample again, calculate the difference. That distribution with so few people, only 5 per group, would be very spread out. You'd see differences, 35 plus or minus 10 is kind of the range of differences you'd see between these two groups. That gives you a t-value of negative 3.32. For the purposes of an exam, I just want you to know that this t-value represents, if you're doing an independent samples t-test, this represents how far away the means are from each other. When you assume the null hypothesis is true, this is a pretty big number in absolute value. I was saying 3.60 something in an earlier slide because this is the same picture. It's actually 3.3, so I was a little off. But basically, after we've got our t-value, 3.32, we ask, what's the probability of observing a negative 3.32 or lower, that's this shaded in area right here, And what's the probability of observing a 3.32 or higher? That's the shaded in area up here. These each are about, separately, they're like a 0.5% likely to observe something this low or lower, or this high or higher. We're doing a two-tailed test, so we want to add those together. You end up with basically 1%. There's a 1% chance of observing a t-value this low or lower, or this high or higher. What do you do when you get a p-value that's this low? You reject the null hypothesis. And it's the same logic as before. We're just retreading the same stuff. Basically, we know our data are true. I mean, this is made up data, but assuming it was real data, when you test the null hypothesis, you say, well, let's say I'm wrong. If I was wrong, this data would be very unlikely, but I know that I saw this data, therefore the hypothesis must be wrong. The null hypothesis must be wrong. Therefore, there must be a difference. There's probably a difference between drinking coffee and drinking a Monster energy drink before going on a speed dating gauntlet. Another important concept from this chapter is a family-wise error rate. And the reason I talk about these family-wise error rates is because it puts a limit on how many tests you can do on the same data set. And that's why you can't just do a bunch of t-tests. If you have more than 2 sample means, like if you have 3 sample means, 3 groups, and you want to know if the sample means are different from each other, statistically different from each other, you can't just do group 1 versus group 2, do a t-test, group 1 versus group 3, do a t-test, group 2 versus group 3, do a t-test. You can't just do a bunch of t-tests. You have to find some way of testing everything at once. Spoiler alert, this is why we have the ANOVA test for later. But a family-wise error rate is, it's basically your risk of getting a type 1 error. We choose 5% as our type 1 error rate. We say, so a type 1 error rate is when you reject the null hypothesis, but the null hypothesis ended up being true. So we say, assume the null hypothesis is true. How likely are our data? If our data is less than 5% likely, then we're going to reject the null hypothesis. That means, we could have used a more stringent criterion and said the data has to be less than 1% likely or less than 0.1% likely. But we're just going to go with 5%. Well, if you're just doing that one test, then you are taking that 5% risk, so to speak, of getting a type 1 error rate. Type 1 error rate is when the null hypothesis was true, but you rejected it. So if there really was no difference between the groups, but every now and then, if you sample, especially if it's a small sample, you might see something that's extreme. Extremely unlikely things happen all the time. Like if there's no difference between the groups, but you just happen to sample some people from each group that are really different from each other, you'd get the mistaken impression that the groups are different when you just got an unfortunately non-representative sample. So we choose 5%. But if you do 2 tests on the same data, that increases your type 1 error rate. I have an equation in the chapter that goes into detail about where these numbers are coming from. But basically, if you're doing 2 tests on the same data, your family-wise error rate goes from 5% to almost 10%. And you can think of a family as like, they all have to live in one household. Each family member is a statistical test. If you only have one person in the household, only one statistical test is going to be run on that household, on that data set. Then there's a 5% chance that you're going to make a mistake. If you have 2 people living in the same house or like working on the same data, 2 tests in the same data, then it's like you're combining the first 5% with another 5%. You're getting almost 10%. This isn't an accumulative adding. It's not just 5, 10, 15, 20. So the math isn't that simple. But that's basically what you're getting. The more tests you do on the same data, the more likely you are to make a type 1 error. And in the real world, some researchers do this. They claim it's not on purpose, but basically they'll analyze their data, not see and they won't see the result that they wanted. So they'll reanalyze the data using a different strategy, trying to force the data to give them the conclusion they want. They'll analyze it all kinds of different ways. Basically, what you're doing is you're flipping the coin over and over again, hoping you eventually get the outcome you want. Or it's like rolling two dice and you're like, I got to get doubles. And that means, my hypothesis is right. You roll the dice once, you don't get doubles. So you keep rolling and rolling over again until you eventually get them. It's like playing the odds. Eventually, if you keep torturing the data are going to yield and give you a false result. So that's why we use an analysis of variance, or ANOVA. And I'll refer to this as a between subjects one-way ANOVA. It's a bit of a mouthful, but it's necessary to be specific. If you're going to be reading psychology journal articles, and if you're ever going to be writing up your own research, you need to be pretty specific about what test you're using. We call it a between subjects ANOVA because this is a situation where you'd have 3 or more separate groups. This isn't the same group being tested at 3 different times. Each person contributes 1 data point in a between subjects design. Later, we're going to learn about other designs where people in your sample contribute multiple observations a piece. So like there might be a before and an after. With a lot of weight loss studies, they'll do before the boot camp, directly during the boot camp, after the boot camp, 6 months after the boot camp. So they'll have different time points for the same group of people being measured multiple times a piece. For this kind of ANOVA, though, every observation is completely unique, coming from a different person. We call it a one-way ANOVA because there's one factor. So you're testing the difference between 3 or more sample means, and these 3 sample means are different along the same category or the same factor. So it can be who has more satisfaction with their degree. Is it business majors, nursing majors, education majors, social science majors? Those are all different majors. They're different groups within the same overall category of major. There's one factor of college major. You could also do an ANOVA on who has more satisfaction with their degree, men, women, or non-binary. That would be 3 or more groups. And the 3 groups are all one type of category or come from the same factor, which is gender or sex. What you could not do with a one-way ANOVA is you couldn't have 2 factors. You couldn't say who's more satisfied with their degree depending on their major and on their gender/sex, because that would be 2 factors at the same time. You'd have to use a different test for that. So basically, the group means, the 3 or more group means that you're testing to see if any of them are different, have to all come from the same. They can be different category members, but they have to be in the same category, is basically what I'm saying. They're all part of the same factor. Like I said, it's used to test for differences between group means or sample means at different levels of the same factor. And I gave a few examples. So I'll revisit my old example. For the t-test, now t-test is only used for 2 groups, 2 independent groups. Before we had coffee drinkers and monster drinkers, Unleash the Beast. Now let's say we had non-coffee drinkers. It's weird to call them non-coffee drinkers because there's 2 other groups that drink things that are either coffee or not coffee. Just cut me some slack. I was not forward thinking when I made this, I guess. But you have people who basically don't drink anything, is what I meant to say. And then they go on their speed dating gauntlet and they get rated for their attractiveness. And then you have a group of people, different group of people, okay? This is between subjects. So we have a different group of people who each go through and they drink coffee before the speed dating. And then you have a different group of people who each drink a Monster energy drink before going on their speed date. So this would be an appropriate time to use an ANOVA because you have 3 or more groups along the same factor. The factor here is, what did you drink? Nothing, coffee, or Monster. And these are independent groups or between subjects. It's a between subjects design. So 3 or more sample means from the same factor, that's an ANOVA, that is appropriate. So this stuff, the equations, I'm not too big into, like, I'm not gonna make you calculate this stuff for an exam or a lab or anything like that. I'm putting them here because it's good to start learning them, and I want you to know the concept, the big picture concept, and the equations are part of the concept. So you don't necessarily have to completely memorize the equations. It just helps if you want to really fully understand the concept, because the equations are part of the concept. So when you have 3 or more sample means, I've got all the scores stacked on top of each other, the no coffee, coffee, and Monster. The first thing you need to calculate is, if you're doing an ANOVA, is the total sum of squares. Just like with regression, this represents the total amount of variation in the dependent variable period. It's the total amount. If you have some model that can like predict someone's level on the dependent variable, in this case, it's attractiveness scores, the model can account for some of the variation in attractiveness scores. It's going to make some misses. No model is perfect. The total sum of squares is the total amount of accuracy you could possibly have in predicting. It's a measure of how spread out the dependent variable is. And just like, I mean, sort of just like with, no, it is like regression, although it's not stated the exact same way in the equation, it's the sum of all the squared differences between each observation and the grand mean. The grand mean, or here's X bar sub grand, that's just the overall average across all the groups. You ignore what group all these different scores from. You just average all of them, all 3 groups. Don't worry about what group they came from. Average them all together. That's the grand mean. That comes out to 68.2. So to calculate the total sum of squares, you go through each score. 67 minus the grand mean, 68.2. You square that difference, you get 1.44. So that's your first squared difference. And you go through each score and square the difference between that score and the grand mean, add it all together, and you're going to get 3,644.4. So this is the total amount of variation and squared variation in attractiveness scores, 3,644.4. Visually, if I took each group, so like here's the first one, it's 68 or 69. This is a non-coffee drinker. They're right below the grand mean. The grand mean is this black horizontal line. It's about 68 or 69 itself. That's the overall mean when you average across all the groups. The second non-coffee drinker was very attractive, just below 90 on the attractiveness scale. So each one of these points represents how far each person was away from the grand mean. And each of these gray lines represents the distance. How far away from you, how far away from the grand mean were you? That's really what the total sum of squares is just adding up the lengths of all these lines. You add all these lines, the lengths of all these lines together, and that gives you the total amount of variation. There's a lot of variation in scores. Add all the variation up, all these deviations from the grand mean, add it all up. Technically, we're adding up the squared deviations here. And you might recall the reason we do that is because the raw deviations would always cancel out and add to 0. So you square them to make up for that. For an ANOVA, what you then do is you look at the between groups or between subjects sum of squares. So you take the mean of the group and say how far away is that group mean from the grand mean. So the non-coffee drinkers are represented by this black bar right here. If you average all these points together, you would get a mean of like 68, 67-ish. It's below the grand mean, just below the grand mean. Then you have the coffee drinkers. That's the red bar right here. So if you averaged the first coffee drinker, the second, the third, the fourth, and the fifth all together and average them, their average attractiveness score would be just above the grand mean at about right here on this red bar. Green bar is the monster drinkers. They all came out to be, they averaged out to be kind of just below the grand mean. And the between subjects ANOVA is basically taking the distance between each group mean. See how these gray lines represent the distance between each data point? Doesn't matter what group the data point came from. Just adding up the distances of all these gray lines represents the total variation. Now you take the distance between these group means and you look at the total distances those have from the grand mean, you can see that it doesn't add up to much. So this is maybe like 2 points right here. This is maybe 2 points, and this is practically 0 points away from the grand mean. So when you crunch these through the equation right here, and this equation is basically the squared distance between each group mean and the grand mean. It's a little more complicated than that, but we'll just call it that for now. That comes out to 23.83. That means that 23.83 units of the total variation is accounted for by knowing which group someone came out of. That is not a lot. And if you reread, I think it was chapter 5 that talked about predictions and like accounting for variance. Think of it like, imagine if I didn't tell you if someone was a non-coffee drinker, a coffee drinker, or a monster drinker. I said, I'm going to run a new person. I'm going to randomly assign them to one of these experimental conditions, one of these drinks. And I just want you to predict what their attractiveness score is going to be. As you can see from all the gray lines, their ups and their downs, it's going to be really hard to predict what their attractiveness score is going to be. And knowing what group they come from doesn't help you much because the group means end up being kind of really close together. So overall, you're not helping much with your predictions because the amount of variance accounted for, the 23.83, is very low. So here's the 23.83 sum of squares. This is called an ANOVA table. You basically take, like, here's the between groups effect, and here's the residual that's left over, and here's the total. So you remember the total sum squares was 3644.4. That's the total amount of variation you could have possibly accounted for. That's all the gray lines added together. And the group level only accounts for 23.83 of that 3644. A very small amount is accounted for by knowing what group they came into. The leftover amount is just the total amount minus the between. 3620.57 is just the difference between the total and the group sum of squares. So in some ways, if you read the correlation and regression chapter, and especially chapter 5 on like predictions and like sum of squares and all that, this should all look pretty familiar. You're basically saying, like, am I able to improve my predictions? If I wanted to predict the dependent variable based on the grand mean or based on knowing specifically what group people came from, is that really helping me? The way you answer that from a statistical testing perspective is you calculate an F value. I go over the details of how to calculate the F value in more detail in the chapter, but I'm more interested in making sure you know the big picture stuff. So, you divide sum of squares for each source of variation by the appropriate degrees of freedom. That gives you a mean square. So 23.83 divided by 2 is 11.91. The ratio of the mean square for the between groups variance and the mean square for the residual variance is just 11.91 divided by 301.71. That comes out to 0.039. That's our F value. The F value represents how much variation on average are we able to account for with our model compared to the amount of variation that's left over, when you don't account for, when you've already accounted for the group. See, why I know what group you came from, I've got, at least this much extra added bonus to the accuracy in my predictions, but there's all this extra stuff that falls short. Like I'm falling short of making super accurate predictions. That's represented by the F value, how much added benefit I get from knowing what group you're in versus what's left over after I don't know what group you're in, or after I know what group you're in, but I still have some error left over. F value is going to get bigger as you have a larger between subject variance that you're accounted for. So the bigger the difference between the groups, the bigger the between subjects variance is going to be. The more between groups variance you have, the larger the difference there is between the sample means, the less leftovers you're going to have. This ratio is going to change. You have a bigger numerator, then the F value is going to get bigger. If you have a bigger numerator, the denominator is going to get smaller, because the more you can account for with the between subjects effect, the less leftovers you have. The bigger the difference between the means, the less leftover difference there is left over that you can't account for with the means. I got a picture of the F distribution. It's very different from the distributions we've been looking at so far, in that it only has positive values. It starts at 0 and goes up from there. An F value can only ever be positive. And when you specify an F distribution, you have to specify 2 different degrees of freedom, one for the numerator, one for the denominator. So this one is based on a numerator degrees of freedom of 2 and a denominator degrees of freedom of 12. So this shape of the distribution will change slightly depending on the 2 degrees of freedom that you plug in. But fundamentally, it's the same logic we've been using with our normal distributions and our T distributions. We're going to put an F value on this distribution, and we're going to ask the same question we've been asking, but about F values instead of T values. We're going to ask, what's the probability of observing an F value this high or higher when you assume the null hypothesis is true? When the null hypothesis is true with an ANOVA, that means that there's no real difference between the group means. The group means are all pretty much the same. So the between subjects, the between groups is going to be very close to nothing. And there's going to be lots of leftovers, because the total variation, you don't end up being able to predict much of the total variation because there's no real difference between the groups. It gives you no basis on which to improve your predictions. So there's nothing but leftovers in terms of predictions. So the bigger the difference between the groups, the larger your F value would be. If your F value gets high enough, you'll be able to reject the null hypothesis and say this is just too unlikely of an observation. When you assume the null hypothesis is true, that I'm going to reject the null hypothesis. So when F equals 0.39, an F of 1 would be about right here. 0.039 is in this shaded area. You can barely see it. It looks like just a line. But this is the bottom, like 0.5% of the distribution. So 95.5% of this distribution is not in the shaded area. It's in this non-shaded area up above. Same logic as before. Basically, the probability of observing an F this small when you assume the null hypothesis is true is basically a 95.5%. It's very likely. So you can't really assume the null hypothesis is false because your data are very likely, 95.5% likelihood that you'd observe this data when you assume the null hypothesis is true. So we cannot, we can't reject the null hypothesis with this data. Now, let's say there was a big difference between the means. Here's a different scenario where I've used different numbers. So you can see the non-coffee group is somewhat further down than it was in the original example. The coffee group, this red line, on average are much lower than the grand mean. They're down in the 50s. And the monster group is well above average, up to about like 86 or so on average. So we have our sample means are further apart. This would result in a statistical test that was statistically significant when you run these numbers. So here's an ANOVA table where I've got the between subjects sum of squares. This is when you're basically counting up how far apart are the groups. This is a much bigger number. It's almost half of the total sum of squares. Is it almost half? I don't think I have that written down anywhere. It looks to be about almost half. So the means are now far enough apart in this new example to where if I had to say, hey, would you rather just have the grand mean to make predictions about what someone's attractiveness is? Or would you rather use what group they came from to predict their attractiveness? Well, now knowing what group they came from gets you substantially closer to making accurate predictions. You can have less error. So the between subjects sum of squares goes up. By necessity, when you've accounted for more variance with the between groups aspect, or the between, like knowing what group someone came from, you necessarily have less leftover variation. So this ratio, the F ratio, goes up. The further apart your groups are, the higher this F value is going to get. The higher the F value, the more unlikely your data is when you assume the null hypothesis is true. So when you change the data to be these new numbers, the new p-value is 0.01. That means that when you assume the null hypothesis is true, there's a 1% chance that you would see a difference this big or bigger on the F distribution. An F value this big or bigger has a 1% chance of occurring when you assume the null hypothesis is true. Since that assumption of the null hypothesis leads to such an implausible probability, then you reject the null hypothesis and you say, there is a difference between the groups. This is called an omnibus test. This is telling you that somewhere between the sample means, there is some significant difference between at least one pair. It's not telling you which pair of sample means are different from each other. It's not telling you whether multiple pairs of sample means are different from each other. It's just saying, among these sample means, at least one group of sample means are different from each other. Once you've rejected the omnibus null hypothesis with an ANOVA, you're then allowed to do something called a post hoc or follow-up analysis. That's when you actually go through the work of figuring out, okay, now that we know that there is a difference somewhere, why don't we go figure out which groups are actually different from each other. You don't want to just use t-tests to do this, because then you'd end up doing no coffee versus coffee, then you do no coffee versus monster, and then you do coffee versus monster. We're back to the same problem that we had before, where we're doing multiple tests on the same data, and that increases our family-wise error rate. So just doing t-tests is not going to help us. If you have first rejected the omnibus null hypothesis for an ANOVA, that gives you permission to use tests that try to correct for family-wise error rates, but you want to minimize your risk of family-wise error rates by showing that, like, testing all 3 or all 4 or all 5, however many means you have, you want to show first omnibus test that there's some difference in there for sure. Now we're going to go in there and figure out what that difference is. You got to do that first. There are multiple ways to do a correction. You're trying to cut down on the probability of doing a type 1 error or having a type 1 error. Multiple ways of doing it. Probably the simplest way to do it is the Bonferroni correction. But whichever correction you end up doing, they all do some form or the other of the following. They just say 0.05 is not a good enough p-value. You can't just get 0.05 or lower. You have to get some more stringent level. Basically, instead of having to be this tall to ride, you now have to be this tall to ride. It's making it more difficult to achieve statistical significance. The simplest way to do this is to do the Bonferroni correction. That's where you take your type 1 error rate, or alpha level as it's called. It's usually 0.05, and you divide it by the number of tests you're going to do. So if you were going to have to do 3 tests on the same data, you divide 0.05 by 3, and you end up with 0.01667. So now for something to be considered significant, it can't merely get past 0.05, it now has to get past 0.01667. So we just made it harder to become statistically significant. Bonferroni correction is nice because it's simple. A lot of people can calculate it by hand. You know, if you get a significant ANOVA test, then you can just say, okay, well, I want to do this many t-tests on my sample means. I want to figure out which one's really different from the other. So just divide 0.05 by the amount of tests you're doing, and then you do all the t-tests, or have your computer do all the t-tests. And then you see if any of those come out to the new alpha level, 0.001667 in this case. A lot of people can do that by hand. Bonferroni correction does have its downsides, specifically if you're doing lots and lots of tests and you have good reason to do lots and lots of tests. It punishes you way too much for doing multiple tests. If you're really not doing that many extra tests, it's fine though, especially if there are big differences. It's not going to change your conclusions. I'm going to end here on the assumptions. These apply to t-test, independent samples t-test, and to the ANOVA we just covered, the one-way between subjects ANOVA. Like I said in the chapter, it's kind of weird to state the assumptions this way, because later in the course, I'm going to show you how really all these tests are basically the same underneath the hood, and you can very succinctly, very parsimoniously state all of the assumptions in a way that's kind of more rigorous and systematic and easy to remember. Just to hold us over until then, there are these 3, there arguably are more assumptions. Like, for instance, I don't explicitly say here there are no outliers, but pretty much every test assumes there's no outliers. For this one, independent samples is the first assumption. That's what I've been harping on this entire time. That means that each observation comes from a unique person. If your unit of observation is a person, a human being, then each person contributes 1 data point. So no before and after, you know, you can't have multiple data points coming from the same person. You also assume that the population distributions are normally distributed. So for an independent samples t-test, it's assumed that the 2 sample means are being drawn from a normally distributed population of possible observations. For both groups, for ANOVA, it's assumed that for each group, 3 or more groups, each one is coming from a normal distribution. And constant error variance, oh, it really hurts me to say it this way. Basically, you assume that each distribution is roughly equal in how dispersed it is or how spread out it is. If one of your distributions has a lot of scores that are pretty much the same, and another distribution has people that are all over the place, then that's not going to be an accurate, that these tests assume that they're roughly equal in their dispersion. So you wouldn't want to just use the normal t-test or normal ANOVA if you know that some of your groups are very narrow in the way they're distributed, low variance, and some groups have high variance. You'd want to use a different test. If you're worried about it, thankfully, there's this thing called Welch's t-test. It's for when you have 2 sample means. What Welch's t-test does is it says, okay, to the degree that the variances are unequal, let's correct for that to make our result closer to the result you would see if they were equal. If you ever end up using R, when you ask for a t-test, always uses Welch's t-test as a default. If you are thinking about becoming a psychologist, a researcher, or if you're just going to be a clinician that's an intelligent consumer of data, or if you're going to grad school, you're probably going to have to do more advanced stats classes. I highly recommend you pick up R. I can help you learn R if you'd like. But the reason R, when you ask for a t-test on some data, it just makes it just, unless you tell it otherwise, it's going to use Welch's t-test. And the reason it does that is because if the variances in your 2 sample means are roughly equal, then Welch's t-test is not going to make a difference. It's going to give you the same result, basically, if you've done a normal t-test. If they are not equal, then Welch's t-test will correct it. So basically, it cannot hurt, but it can only help. So that's why it's the default when you use R. Well, that's all the energy I have for this. How long did that take? An hour? I don't know. But I need a break. You probably need a break. You get to pause this if you want to. But until next time.